Oh, well, hey there, everyone. Welcome, welcome, welcome to Astronomy Daily Live. I am not only live streaming, but simultaneously, I am making sure that this wire is not being chewed and carried around by my kitty, who definitely uh, wants to grab it and make off with it. But what this is actually probably one of my favorite. Now, I don't really think that you need to be here. Come on, we're trying to do a live stream, and you're just totally distracting us. Anyway, this is a great and probably my favorite red light of all time. It's variable in brightness. It's got this little dial here. I cannot see anything here. You have to see. There we go. All right. And so it's switch off, and then switch on to a really low level, and then it can get really really bright. But it's still red, so it actually I've tested this out here where it's always extremely dark, and yeah, it definitely does not ruin my night vision or anything. And the label on the side, which I don't know if this is who made this or not. I got this from a friend, wow, 10 years ago or so. But it's, let's see if I can get that to focus. There we go. Starlight. Rigel Systems. So, I don't know, but yeah, I've used this extensively, and works really, really well. Works really, really well. Like I said, you can throw out a little bit of light, right, or a whole bunch, and it's pretty awesome. Anyway, but it also makes for a great top-notch kitty toy. Just one of the best ever. No kitty can possibly resist that. Just no way. Absolutely no way. So, with that said, welcome all to this live stream. What is this? This is the 15th of October. No, the 16th of October, 2018, and it is 2:03 UTC. Astronomy Daily Live. So come on in, friends. Welcome. In the panel, once again, we have Bobby. Hey there, Bobby.
Hey.
And also Tom is in the panel. Hey there, Tom.
Hey, Cosmic. How you doing?
Doing well. How's life out there?
So far, so good.
Good. Yeah, all is well here. It's been cloudy and rainy here for a few days. We last week we had the remnants of a hurricane come through, and then a few days ago we had the remnants of a tropical storm come through, and sort of since then it's been just sort of cloudy and rainy and foggy and all of that here. So pretty typical for this time of year. So no big deal, but definitely not clear skies in the least. So, all right, well, hope everybody's doing well. I'm going to look at my chat, which I think, yeah, I did pop that up. Yay. So Atta is in the chat. So Mokai said, Explorer Scientific RL02317 is the best red light he had ever used. Okay. Yeah, I think you know, red light is red light. So as long as you've got one, I think you are good to go for sure. This is just one that I've had for years and years and years, and haven't. I don't think I've even ever. I don't even know how to replace the battery on this thing. I have absolutely no idea. I don't think I ever have. So that's saying. Well, I don't know if that's saying a lot in terms of how little energy this uses or how little I use it. I don't know. I use it a lot though, so I don't know. Anyway, tonight I definitely have the hydrogen hydroxide again. A nice full mug here, and got some nice hot coffee here too. So cheers.
And it's been like raining and stuff, and well, it's not raining, but right now, while I was outside at the nighttime, it was like just a little bit of thundering.
Wow, wow. Yeah, yeah. Well, I guess 'tis the season. So, yeah. Typically, we'll, here we don't get any kind of hurricane type of anything because we're way too far um, um, inland. But we definitely get the remnants. I remember several years ago. I think we had four remnants barrel through over the course of a couple months, and it rained. It started raining monsoon in July, and it really didn't stop raining until like the end of November. So it was a wet season. But and us desert folks, Tatooine types or Mars types just aren't used to all this water. There's just so much water everywhere. We just don't know what to do with it all. So, so Atta's saying that the experienced observers in her club say that the best time to observe is winter. Winter in the northern hemisphere. Well, let's say this, okay? Winter has one advantage, and that is a longer night. A longer night. Winter in the northern hemisphere, typically you'll have a lot more bright stars. The summer sky in the north, while we have the Milky Way and all that, there aren't a large number of bright stars. In the wintertime, there's a few more. But if you live in the south, of course, they're experiencing their summer. So it's sort of a reverse thing. So I think I have to sort of disagree. I don't think that there's a good time or a bad time to do observations. It sort of depends on what you're looking at, looking for. But every season has its really, really great things, and things that it's like, wow, I wish I could see that now, but it's not up. So yeah, I don't think it's a matter of best or worst or anything like that. That's sort of a subjective thing. The sky is absolutely amazing, right? And there's always some pretty incredible things to either observe or collect data on, whatever you're doing.
And when you did your observations live, you also like did around the summertime as well, if I recall correctly.
Oh, well, the only reason why that has happened is mainly because you know um, 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 that's when I've been doing this live stream, right? I mean, I guess I started in January. I think I did an outdoor live stream. I want to say somewhere in February or March. I think was the first one. I don't remember exactly, but yeah, the disadvantage to uh, the winter sky, uh, at least, well, yeah, I mean, regardless of where you are, is that it's cold, right? It's usually kind of cold. While in the summertime, it's, can be pleasant. Now, heat causes, other kinds of problems in terms of seeing and all of that. But so, yeah, I would say the main disadvantage with the winter sky isn't the sky at all, but actually just the climate. It's just it's just cold, right? And it's long and cold. So yeah. Like I said, I disagree that there is a best or worst time. It sort of depends on what you're after, right? And that, I mean, in truth, right? Except for um, maybe like the hour and a half um, um, west of the sun and the hour and a half east of the sun. So, except for a 3-hour gap, right? Um, we can see the entire sky in one night. Is that true? Can we see the entire? No, we can see. How does that work now? I'm trying to think. Yeah, we could see, except for that gap, right, where the sun is. Over the course of one night, we can see the entire sky. So 21 hours of right ascension is always accessible to us. So that's another thing that you sort of have to think about, right? Is that in the summertime, what you're calling a summer sky? Well, it's a summer sky, maybe you know um, in the early evening, but in the early morning, it's a winter sky, right? So even that is sort of a confusing term. Um, so yeah, you sort of have to clarify, you have to specify. But having said that, there are objects or classes of objects that are up during the summer or the winter, and if that's what you like, then that's probably your favorite season. Hey there, Andy. Nice to see you in the chat. Oh, this is actually, it's a little bit warm here. All right, cool. So, yeah,
Did you see the latest Hubble update from Christian Brady?
the one that came out a couple days ago.
Yeah, something like that.
No, I forgot again to look at that. So I did notice. I think Tom posted an article about it, and I had heard about it earlier that Chandra is coming back online. I forget exactly what the details were, but there was some kind of reading that wasn't exactly right, and so they put it into safe mode. Do you remember anything about that, Tom?
Yeah, Chandra had a gyro that gave some bad data, some bad readings, and so the system automatically went into the safe mode until they could figure it out. I believe they switched that gyro to standby and brought a different one online, and that one seems to be working. So I think they're back in business doing their science.
So they're using their backup gyro on that one. Is that?
Yeah, at least one of the backups. I didn't actually see if it said how many they had and how many were still working, or backups, but they did switch it out, right?
Yeah, nice. Chandra has been up there in orbit for, wow, quite a while too. I'm trying to remember. I'm not going to share my screen. I'm just going to go and look and see when Chandra was launched.
Yeah, that's what I want to know too.
Well, we're going to find out. Chandra.
Because I've never heard Chandra before.
Yeah, that has been around for quite a while.
Well, Chandra is an X-ray telescope, so you don't always see the same kind of real pretty pictures that you get out of Hubble, but it does do some very good science.
Yeah. It's just looking in the X-ray, you're usually looking at high energy kinds of things.
I just got a question about Chandra.
Okay. Anyway, Chandra looks like it was launched on July 23rd, 1999. So it's been going for almost 20 years or so. So not bad. Not bad at all. And yeah, I guess I haven't followed it as closely as I probably should. I don't know if this is the first sort of problem that they've had in terms of things breaking down, because if it is, that's pretty good, right? Not too bad.
Haven't heard much other troubles from this telescope.
And
ATA is
kind of weird. It's kind of surprising they just turned on the Chandra after quite some time. Why did they turn off the Chandra for?
No, it's been going for a long time, Bobby.
Yeah, it's been going for 20 years or so. So yeah, it's been doing really, really, really well this whole time.
And ATA is correct. That telescope is named after Chandrasekhar. I think that was his full name.
Yep.
I believe he is the scientist who discovered the critical mass.
Yeah. The critical mass between whether a star is going to evolve into a white dwarf star or a neutron star, and it turns out that number is about 1.4 solar masses. So our sun is at least according to the theories is going to turn into a white dwarf, because it doesn't have quite enough mass to when it runs out of nuclear fuel, right? That core is going to start collapsing under the weight of all this stuff, right? But there isn't enough to actually squeeze that core to a neutron star. It's merely going to be a white dwarf star, which is exciting enough. But yeah, the magic number there, which is called the Chandrasekhar limit, is 1.4 solar masses. And then somewhere, and I don't think that there's a sort of a hard limit to whether a star is going to become a neutron star or a black hole. But it's somewhere around like 5 or 6 solar masses. Stars that are between 1.4 and 5 or 6 solar masses so the theory goes, are going to turn into neutron stars, and then any star larger than 4, 5, or 6 or 7 solar masses, at least the math says that they are going to supernova and turn into a black hole. Neutron stars can also be produced by supernova as well. So yeah, this spacecraft was named after Chandrasekhar. I think that was definitely the right thing to do there, for sure. So let's see.
It's kind of a bit weird about that dude that the boys in the scientific community made fun, but he didn't give up and was vindicated at the end. Was not only brilliant, but also was courageous.
Yeah.
So he showed them that he's got the stuff.
He's got the stuff. He's got the stuff. I wish I had a little bit of that stuff. Yeah, I don't know where that comes from. Yeah, that's. Yeah, I don't know much of his story, but yeah, he was a brilliant scientist and did some good stuff. So yeah, I should probably learn a little bit more about him. But yeah. Good stuff for sure. Cheers to Chandra.
If I was get done with any criticism, I would say just keep on, and maybe when you meet your maker, you will go straight to the outer darkness.
There you go. Absolutely. So, I think what I wanted to do was sort of finish up with IC 1613 tonight. The one thing that we didn't do yesterday was look at all those references. Because it's sort of a dwarf galaxy. We've looked at it. We've looked at some pictures of it. And it's sort of a loose association of stars, but it seems to have sort of an unusually large number of papers that supposedly mention it. So I just sort of wanted to go through those. I definitely don't want to go through each and every one. Right? There's over 1,000 of them, but I wanted to sort of scan through those a little bit, like we do, and maybe sort of get a sense of, what's so interesting about this particular dwarf galaxy. It's a member of the local group. It's pretty close. It's about as close to us as the Andromeda Galaxy is. But besides that, what else is going on here? So let's just go right to the horse's mouth and see what the papers say. So I'm going to share my screen and go over here and go over here and go to here. Okay. So this is where we were yesterday. But yeah, like 1,031 references. So let's take a look and see what's so exciting about this. I don't know. I mean, it's all, all things out there are really, really cool. But it's like, well, what's so interesting about this that it's gotten so much attention? So this list is really, really nice because it's in chronological order, right? So the latest paper is up at the top, and the oldest one is way down at the bottom here. 1936 is sort of the first reference there is to it.
1936, that's got to be old.
That's pretty old. Written by Edwin Hubble himself. Huh. Let's take a look at a paper written by Edwin Hubble. This is the Hubble.
Yeah.
If we can. You must have confidence, Bobby. You must have confidence. Oh, well, my internet's being really, really slow. That does not bode well. See that? Bobby, you're jinxing us. Can't do that. I think my internet is being a little bit slow. So, yeah, you know, we just...
Join some DSL. Should have got cable.
Yeah, well, I do not have access to cable out here. I am too remote. Wires won't go long enough.
No 4G or satellite?
Satellite is pretty terrible here. I guess probably the 4G would work, but I'm all right with what we've got. Let's see. Wow. So this was written by Mr. Hubble himself. So I can't possibly imagine that he talked about IC 1613. I can't imagine that. But oh wow, look at that. He did. So wow, back in 1936 they knew about this dwarf galaxy. Wow. Okay. That's pretty fantastic. Pretty nice. Let's see. There are 3 mentions of this. So let's look at the next one. So the data for IC 1613 are derived from unpublished investigations by BOD. Those for M31, M33, and NGC 6822 from star counts by the writer. Okay, so doesn't say much there. Let's see what the next reference is. Resolved nebulae in the local group and the general field. Wow, okay, so I think, let's see, M sub S, have to understand what these things mean here. Let's go back up and see if we can find out. So yeah, here again they're talking about M sub N and M sub S. I'm gonna have to go into the paper to find out, I think, what's going on here. Let's see if we can find out. Oh, come on. In astronomy, you have to learn patience. Not only patience with others and instrumentation, but most importantly with yourself.
How many pages are we looking at?
I don't know. There seems to be about 1 trillion of them. I'm just trying to see if there's any... There's got to be a description somewhere, and I'm just not seeing it here. Okay, so the frequency distribution... brightest star, arbitrarily defined as the mean of the 3 or 4 brightest individual non-variable stars in a nebula, is calibrated as a criterion of distance. M sub S.
No, it's kind of a bit strange. It starts at page 158, but you're actually on page 1, which means it might have been scanned from a book or something.
Yeah, oh yeah, yeah. You know, this is taken out of a journal, which yeah, is you know, going to be at some page that isn't the first one. Yeah, I'm not quite sure what this M sub S, M sub N stuff is here. Huh. Okay. Well, I just think it's kind of neat that it was known about and observed and measured and all of that. That's kind of neat. That's kind of neat. And he actually looked at quite a few nebulae, which we now know are mainly galaxies. I recognize a few of them here. 7331. That's a nice one. Let's see, are there any others that I sort of recognize? Not really. They don't seem to be in any particular order. Well, I guess the M sub S here, it's being ordered that way. Huh. All right. Well, anyway, that's kind of neat. That's kind of neat that it was mentioned here. So let's see. All right. So let's go up to the top, and we will just do another search for 1613 and see if it comes up here in our list. The near infrared tip of the red giant branch. Okay. Quantitative spectroscopy of supergiants in the local group dwarf galaxy IC 1613. Metallicity and distance. Okay. The distance to IC 1613 based on RR Lyrae period luminosity relations. Cool. So yeah, I'm doing a search just looking for that object name in the title, right? Because then we sort of know for sure that it's like, okay, this is exactly what they're talking about. Multi-wavelength observations of 2015 nova. Okay, so there was a nova in that galaxy back in 2015. That's kind of interesting. Let's see what that's all about. Discovered 2015 September 10 and is the first nova in that galaxy to be spectroscopically confirmed. That's kind of cool. Let's see what else we got here. We can.
And what year is that paper made?
We'll find out here. Oh, here it is. Publication date December 2017. So just a couple of months ago. Pretty new. Talking about a nova that.
Or a couple of months, it'd be just about a year old.
Almost a month. Yeah. Almost a year. Well, this is just taking its sweet old time here. While it's doing that, I'm going to take a sip of coffee. Oh, it's slowly loading. We need some loading music.
Yeah, some nice either that Jeopardy theme song or elevator music. I'm still wanting to work on a way to pipe some sound into this this stream. I think that would actually add some nice Maybe
ambiance.
On the post show, I want to look at the sound options again on your system, and I want to check and see if you do need to like switch to a different environment and stuff. Yeah.
All right. Yeah, we can do that. Anyway, let's see. So let's see. This was observed at Siding Spring at the 2-meter telescope of Las Campanas Observatory. That's what LCO is. I think. Let's see. The Liverpool telescope, the LCA. Okay. I see. So observing with this telescope and this telescope and Swift. Cool. So the nova peaked at a M sub v, which is a absolute magnitude of negative 7.93. So what that means is that if this nova were 10 parsecs away exactly, then it would have a visual magnitude of negative of 7.993. In truth, right? I mean, it's pretty far away, so its actual visual magnitude was probably pretty darn faint, pretty faint. But a pretty fast, I guess that's a pretty fast decline time, as they call it here. That seems a little fast. So, okay. It looks like they took some spectra too. Yeah, nice, nice. So yeah, that's kind of an interesting thing, right? Is to collect spectra over time and see how things change, right? How the hydrogen absorption changes. They're talking about iron and nitrogen lines here. See how those change over time. It's kind of interesting, and it can tell us all kinds of things about the dynamics of what's going on. And of course, we like to feed all this information into our models and see how well the models behave as well. But yeah, it just so happens that this nova occurred in our little dwarf galaxy here. So, relatively close. Yeah, there it is. So as you can see, well, I mean, maybe it isn't extremely apparent, but that's a pretty faint little star there. Pretty faint. Yeah, so it sort of looks like they just sort of go through the same recipe as most of these kinds of papers, right? They sort of lay out what they heard, sort of the history, all of that, and then they get into what observations they made, what kind of instrumentation was used, different observatories, different filters, wavelengths, right? Some spectroscopy stuff. I always like to see links here because that usually means that there is data available. Well, I'm not exactly sure what that is. IO:0. Not quite sure what that means. Let's, can we do this? Not quite sure. It's one of the things that we do, though, in this live stream is we follow our noses a little bit. So IO:0 is the optical imaging component of the infrared optical suite of instruments at the Liverpool telescope. Okay, cool. Sweet. Okay. So yeah, they did spectroscopy too, which is nice. Always like to have spectroscopy if we can, because it provides us with just so much information that we just can't see if we're just taking pictures. Let's see. So photometric evolution. I'm waiting for. Here we go. So So here's the brightness, right? The apparent magnitude of this star by date. And my guess is that the different colored dots here are probably the different filters used. Yeah. So let's see. The cyan, sort of this, I guess this bluish one here, is what's called U prime. The purple one is B. Is that this one? I guess so. Let's see, the blue. Am I reading this wrong? Yeah, I'm sorry. So this filter called UVW1 is the cyan. The U prime is the purple. B is the blue. V is the green. R prime is orange. I prime is red. Z prime is gray. Okay. And H is black. So H is far in the infrared. I and Z are sort of in the infrared too, for sure. So you can see that sort of in what I would call the visible bands. These guys here, they all sort of keep the same track, right? But let's see, this orange one here, this orange one, the R prime, look at that. That's staying brighter, right? They all look like they start, like about the same point, but then these guys dive and fade out pretty quickly. While this one is, staying pretty bright. So kind of interesting. Let's see, the magenta star shows the unfiltered discovery magnitude. Where is the magenta? Oh, there it is, right there. And let's zoom in. Okay, so that's where they first saw it. So they actually discovered this just a little bit before the peak. Now, whether this was the actual peak or maybe the peak occurred slightly before that, we don't exactly know. What we do know, of course, is that on this date it was that faint, and then it got brighter.
So this is just like the light curves, right?
These are the light curves, yeah. So you can sort of see on the bottom here, they show the number of days after the discovery, right? So this goes out, 3 months or so, something like that. And it looks like they've also marked when they took spectra as well. So it looks like they took spectra on 6 different occasions. So that's pretty nice. But as you can see, this dude is faint, right? I mean, at its brightest, right? It was magnitude, and they don't, do they say which? Well, yeah, I mean, it sort of depends on the filter, right? So let's just look at the brightest one here, the green. Well, technically, I guess the black one here is the brightest one, but let's look at this peak, at least. This green is which one? So the V magnitude, what, about 16.65 or so? So, I mean, that's really, really, really faint. And that's as bright as it got, right? I mean, it got all the way down. They stopped observing it, and it was fainter than 21st. So, yeah, that's getting pretty darn faint. But like I said, if it was set at 10 parsecs away, it would be significantly brighter, almost as bright as the moon. Okay, so here's the photometric curve. We also have spectra, right? All these guys here. So let's take a look at those. They probably have some spectra here. Okay, so here's the first one taken on September 12th, early on September 12th, 1.59 days after discovery. And, kind of interesting, there's hydrogen alpha and beta emission and hydrogen gamma and delta absorption. Kind of interesting. Not quite sure what this feature is out here either. Maybe we'll learn a little bit more here. So, okay, so this was the first spectrum taken. And then here's a few more. And as you can see, of course, the brightness drops, right? And that's why this black one, was taken 6.5 days after the event. Gray one a little bit further out, red one a little further out, blue one a little further out. And if you start looking at the individual lines, the intensities of the lines change, the shapes of the lines change, their width. You definitely know that it's like, okay, here are the nitrogen lines, but look, I mean, at day 14, it's almost gone, right? I mean, it's kind of hard to tell if that's a line there or if it's in the noise. Kind of hard to tell. So, neutral nitrogen just sort of vanished. Don't know where it went. But yeah, lots of lines identified here.
It just happened out for some whatever reason, right?
Yeah, I mean, obviously these things just don't vanish into nowhere. They there's some kind of a process that is making them no longer visible. So for whatever reason, they get buried. Yeah, I don't know. I'm certain that there are probably explanations, but I don't know them. You can definitely see, the hydrogen seems to stick around, and the shapes of those lines don't seem to really change all that much. But yeah, lots going on here. They're looking at sodium, helium, some oxygen. Here's some iron. Pretty cool. So yeah, it's kind of interesting to see how the what we're seeing in terms of constituents and other properties. Like I said, the widths of these looks like maybe they change a little bit. The shapes definitely do, right? And all that has pretty significant meaning. Most of which that flies over my head quite a bit. I would have to refamiliarize myself with a lot of that in order to talk about it too much, at least. I just sort of like to see how these things evolve, and yeah. pretty interesting. There, you know, I'm really not seeing any like huge changes here. You know, things get fainter, but you know, basic shapes and locations and all that, yeah, they're pretty much all there, all the way down. So pretty cool, though. Let's see. So this is the final one that was taken on almost November 7th of 2015. Okay, this shows the nova in the nebular phase. So we're starting to get some oxygen 3 here. Pretty cool. Pretty cool. Okay, so here is the evolution of the H alpha line, going from brightest to faintest. So, okay, you know, looking at it this way, right, things do seem to change a little bit, right? The location of this line, right? I mean, you sort of look at the location of the black one, right? It's pretty much right at this 0 point here. But the gray line looks a little off of that, right? And the red line maybe a little bit more, and then the blue is over here. So, you know, are we seeing red shift and blue shift here? Yeah, I mean, sort of, you know, seems like what it looks like to me. So kind of cool. Kind of cool. Yeah, kind of neat. I'm not going to get into this much. So this is the intensity ratio between the H beta and H alpha lines. So early on, it's pretty low, but then, wow, that significantly changes. So if the ratio here is going up, that means that H alpha is either getting larger or H beta is getting smaller. Don't know which one. We can actually go back and I don't know if we can see those. Yeah, that's way too overexposed. You know, the peaks of these are way up above the screen here. So yeah, unfortunately, we're not going to be able to confirm or deny these plots, but I suppose we have to believe them.
So it's just overexposed. It's not in the noise and stuff, right?
No, you know, those lines are just really bright because there's a lot of hydrogen, right? Lots of hydrogen. So yeah, just too bright. But obviously, you know, they measured it anyway, and I think these plots, right, are probably just being presented like this so they can show a significant number of lines as opposed to, you know, just the hydrogen lines. See how in this plot the hydrogen lines, they sort of dominate, right? I mean, there's all these other wiggles here, but these are really strong. Well, this is the same.
The amount of info that can be gained from spectra is truly amazing. I think of spectral data as the DNA of the universe.
Yeah, it's you know, think of it. I mean, maybe DNA. You know, think of it like a fingerprint, and a fingerprint that can change, right? And does change. So you know, taking a spectra at one time is going tell you all kinds of things about, you know, what this object is made of, how it's moving, if it has, you know, magnetic fields, its rotation, temperature, yeah, just tons and tons of info, and to watch them evolve like this after, you know, some kind of an event, you know, like a nova, is you know, you can learn a lot about how these nova sort of operate by looking at this kind of data and making all the measurements and everything else. But yeah, this ratio is kind of interesting. I'm not quite sure what it means, but it is kind of interesting that, you know, it started low and went high. And like I said, I'm not quite sure if that's because the H alpha got larger or the H beta got smaller. Can't tell by this, at least.
And how come they did not dismiss it? The referees did not dismiss it and stuff.
Huh? I'm not quite sure what you mean.
Like the review board didn't dismiss it. They just went up ahead and put it in the journal.
Well, my guess is, Bobby, that if we were to actually read this paper, they would probably talk about that, right? In fact, we can do a search for figure 7 and see. Yeah, so let's see. In figure 7, we show the evolution of the H alpha to H beta ratio between those days. Let's see. So the evolution can clearly not be caused by dust, as such a dramatic change would be seen as a dip in the optical light curve. Nova has been discussed previously. Self-absorption. Okay, that's kind of interesting. I've never heard of this, but let's see. If Lyman alpha and H alpha have high optical depth and a high H alpha to H beta ratio, such as those observed here, can be produced. Okay. Also indicate that the ratio does not necessarily change dramatically during this H alpha H beta evolution, although this is dependent on the Lyman alpha optical depth. Yeah, I'm gonna have to think about that a little bit. Yeah, not quite sure. Not quite sure. But yeah, you know, I mean, obviously, you know, this figure is discussed in the text, and you know, the referees and all that said, yeah, sounds okay to us. Okay, so they didn't see any X-ray emission. And okay, yeah, so they were trying to see if they could see this star, you know, in sort of past observations. And unfortunately, yeah, it was not covered by any of the data from the HST. And the HST would probably be the only one to really be able to see this. Yeah.
Get that out the water. And if you're planning on streaming it, just do it.
Let's see. I have to keep up with the chat here a little bit. see what's shenanigans are going on there. Yeah, early day. Early day. All right. Take care,
Not a
Atta.
lot of shenanigans tonight.
No shenanigans. Too
Not
bad.
tonight.
All right. Well, cool. Let's go through it. Maybe a few more of these. And it's pretty amazing, though, right? I mean, this is just a little dwarf galaxy that's gotten a lot of attention, tons of attention. But yeah, I mean, understandable, right? I mean, it has a nova in it. Yeah, it's going to get a little bit of attention there, for sure. Properties of 10 O-type stars. Okay. Cepheids. The star formation history of IC 1613. Huh. Low metallicity OB type stars. Doing more spectroscopy there. The nature of WO stars. A quantitative analysis of the WO3 star DR1 in IC 1613. Whoop. Huh. I think we've looked at WO stars before. Yeah. Wolf-Rayet stars. Most evolved stars. Yeah, these are stars that are about to push the button. Do something exciting. So a quantitative analysis of one particular star in this galaxy. Pretty amazing. We'll take a look at this. I'm noting the time and can't believe it. Can't believe it at all. So star DR1. Wow, there's a lot of info here. Quite a bit. Observations they made. Huh. So there's some spectra. Let's see. Optical near-infrared spectrum. Okay. Showing sort of the typical lines. Helium, carbon, oxygen. Pretty cool. So let's see. This is going from about 3,000 angstroms to 7,000 angstroms. And this is sort of picking it up there and going out to 20,000 angstroms. So yeah, this is way into the infrared. In fact, yeah, these purple bands here are the absorption bands caused by the atmosphere, the Earth's atmosphere. So these bands, I think I can say, are completely not accessible to us on Earth. You got to be out in space in order to see those. I think, pretty sure. Yeah, spectral analysis is just it's almost voodoo. It's pretty amazing stuff.
Yeah, there's an incredible amount of data on just this one star in this,
Yeah, it's just a crazy amount of work. I mean, it's hard to imagine. I mean, I come back to that all the time. That it's just, I mean, doing this kind of stuff is just Work, work, work. This is hard, hard, hard stuff. But they do it, right? It's amazing. Lots of things are learned. Line ratios. Yeah, just amazing. This looks like a pretty good...
Now, they do have a legitimate reason to approve this because of so much data.
Yeah, I mean, most papers are going to be accepted. Most of them are. A lot of them, they sort of have to go through a little bit of the process and be, modified and revised and all that kind of stuff. But I would say most papers are accepted and published. Most of them are. So you can't really judge based on the content, right? It's like, okay, well, I'm not interested in WO stars, so I'm not going to publish this. Well, that's not really fair. You got to keep an open mind. So even if you don't understand what these objects are, I mean, if you look at sort of the quality of the work, right, and not exactly, or specifically, right, what they're talking about, but if you sort of look at the quality of the work, you look at the authors, where they're coming from, you can check them out in terms of other papers they've written. I mean, you get a pretty good sense that, even if you don't, being a referee, even if you don't totally understand, what the paper's about, I mean, as long as all the work is there and, all of that, it's like, well, sure, let it pass. Let us take a look at it and, see if we agree or not. That's what science is all about, for sure. This is actually a pretty, I mean, if anybody was, sort of interested in spectroscopy, this looks like a pretty good paper to work off of. It's pretty thorough, and it looks like they go through quite a bit of the analysis needed. So this would, might be an interesting one, to pick up and try to learn a little bit from. So pretty good paper, I would say. All right, well, cool. I can't believe that it's already been over an hour, but it is. So, strangely enough, I started this live stream with a kitty in the lap, and as soon as I started, she's like, "Oh, I'm gonna go." Well, she just came back and just plopped herself right down in the lap here. So I guess I must be done. I must be. That's all I can figure. So cool.
Your
Let's
cat is complaining.
yeah, she is letting me know that it is time. It is time. See, I no longer need any communications. I just got to have the kitty here saying it's time. It's time. So yeah, let's get out of here for now. I think that was a pretty good tour of the dwarf galaxy IC 1613 in the constellation of Cetus. We're still sort of in the Cetus mode. I think I want to give it one more day. We'll hit some galaxies and maybe some binary stars, and then we're gonna move out of Cetus. But yeah, as with most things in science, There's so much, right? I mean, one could spend decades, right, just on one little thing, and scientists do that, right? You know, they'll spend their entire lifetimes looking at one star because there's just so much there. Yeah, it's absolutely amazing. So, all right, look at that, chewing on wires and everything. You're in trouble. Yeah. All right. So I'm going to get after this kitty for chewing the wires, and I'm going to get out of here for now. So thanks for coming in, everybody. Make sure to subscribe if you haven't already. You can hit the thumbs up, thumbs down, make some comments, share this around. You know, we talk astronomy here for, you know, about an hour each day. And yeah, let us do it again tomorrow. All right.
Okay, thanks.
Yep. Take care, everybody. I will see you on the spin. See you later. Bye.
Later.